Episode 6, Chemicals. This industry is perhaps the most obvious for chemical engineers. We make chemicals. When I say chemical, I know what you're thinking. A hazardous substance that you'd probably see in the chemistry lab, such as acids. Hydrofluoric acid, for example, was made famous by that one episode in Season 1 of Breaking Bad. Nitric acid, acetic acid, sulfuric acid, citric acid, and butyric acid. These all sound like you'd only find them in the chemistry lab, but the chem lab isn't the only place that you'll see these chemicals. You probably have some in your kitchen right now. Vinegar, for example, is nothing more than an aqueous acetic acid solution, while citric acid is sometimes added in foods to make them taste citrusy. Remember the question from the previous episode about how they make powdered lemonade mix taste like lemons? You guessed it, citric acid. Also in the chemicals class are solvents. Some examples include tetrachloroethylene, acetone, toluene, dichloromethane, or DCM for short, tetrahydrofuran, or THF for short, chloroform, and dimethylformamide, or DMF. It's easy to forget about chemicals like this when I think about chemical engineering, because none of them are readily available to consumers. While perusing the shelves at my pharmacy, for example, I've never found a bottle of tetrahydrofuran. However, some of these are disguised as other things. For example, nail polish remover has acetone in it. That's the primary component. Toluene, as I previously mentioned, is the main component of paint thinner. Regardless, all these chemical solvents are crucial in the production of other products and chemicals, so they're very important. However, if you really think about it, the word chemical can mean anything with a molecular formula, which is, of course, literally everything. Here's another example that I love to use. Oxygen is a chemical produced by chemical engineers as well, often used in breathing apparatuses for the elderly. How do you think chemical companies make the oxygen to put in tanks? While it's true that O2 can be produced by a chemical reaction, there is a much cheaper and more readily available oxygen source: the atmosphere. The only issue is that air is only 21% oxygen. So in order to be effective, engineers need a process that separates oxygen from the other 79%, which is primarily nitrogen. Separation processes is another title of a future course you'll take. Modern technology has figured out a way to separate oxygen from nitrogen right in a device that you can wear on your hip. This oxygen concentrator uses a membrane for separation purposes. Nitrogen passes through pores in the membranes, while oxygen cannot fit through these same pores. This allows the device to deliver 95% pure O2 right to your nostrils. Looking at this diagram and all the chemical engineering sounding language, it's not too difficult to imagine a chemical engineer's involvement with this invention. Polymer materials have diverse applications stemming from their material properties. Not only are chemical engineers involved in producing these materials, but when I look at them, I can see how chemical engineers use these materials in various applications as well. For example, styrofoam is a very cheap material, good for insulation. You've probably seen a styrofoam cooler on sale at your local grocery store. Why is styrofoam a good insulator? Because it traps a lot of air, and air has a very low thermal conductivity. You'll learn more about this term in your heat transfer course. Another example is PVC, often used in residential plumbing because these pipes are cheap and flexible yet rigid, and safe as well. Studying how fluids flow in these pipes will be the subject of your future fluids course. Yet a third example is polytetrafluoroethylene, or Teflon for short. It's often used as a coating on pans to make your food slide nicely out of the pan without sticking. And thermodynamics can explain the hydrophobicity behind this. Another example that really fascinated me when I came across it recently was when I had to replace my air conditioner earlier this year. I remember learning about refrigeration cycles in my thermodynamics class, but for some reason I had never drawn the connection from class to real life, and looking into how my new AC unit worked really fascinated me. When most people think of air conditioner, you probably only think about the big cube that goes on the side of your house. But this part is only the condenser part of the cycle. In the condenser, refrigerant flows through the copper coils that serpentine back and forth on the sides. Copper is the material that these are made out of because it's a very good conductor of heat, and a fan at the top draws air over the coils to remove heat from the refrigerant, which condenses it, as the name condenser implies, from a vapor to a liquid. Afterward, the liquid refrigerant flows through an expansion valve where the pressure is reduced and the refrigerant gets very, very cold. Then it goes to your air handler, which is probably somewhere inside your house or in your garage. The air handler propels warm air from your house over the coils in the evaporator. Energy is transferred from the air to the refrigerant, and as a result, the air gets colder, goes back into your house, while the refrigerant vaporizes. The refrigerant is then pressurized and sent back to the condenser to start the cycle over again. What is the chemical identity of this refrigerant? Given what I just told you about the refrigeration cycle, the refrigerant has to have some very particular properties. For one, the freezing point has to be very low, since you never want it to freeze inside the pipes. That rules out water because even in Gainesville, the outside temperature can dip below the freezing point. It also has to have a high heat of vaporization to maximize the amount of energy it can remove from the air. It must also have a high critical P&T, since beyond the critical point, the substance exists neither as a vapor or a liquid, but rather as a supercritical gas that cannot condense. It must be non-corrosive to the copper pipes and have a high vapor density, again so that the efficiency of the energy transfer is maximized. In the olden times, a chemical that had all these properties was chlorodifluoromethane, more commonly known as R22 or Freon. Unfortunately, you've probably heard about the adverse environmental effects of Freon, which has caused it to since be replaced. Indeed, modern air conditioning units that you buy today all have a different refrigerant, which is called R410 or Puron, and contains a blend of a few different molecules. The setting of chemical manufacturing occurs in the chemical plant, which is chock full of pipes and process units. We will draw plenty of process flow diagrams this semester, including simplified boxes and arrows. But keep in mind what these boxes and arrows actually represent. To get a feel for what a chemical plant might look like, I strongly encourage you to go to YouTube and type in the search bar chemical plant tour. This will bring up plenty of videos that are all very informative. The companies that you can work for in this space include the Dow Chemical Company, which recently merged with DuPont, BASF, Ascend, Evonik, Airgas, and 3M. While you've probably heard about some of these companies, I'm willing to bet that you haven't heard about all of them. Go see them at the Career Showcase this year. This will conclude this episode. I'll see you in the next one.